Hello and welcome to Chemistry with Mr. Olson. Today we're going to do some problems from our worksheet, the nomenclature worksheet. And up at the top of our worksheet is a table of polyatomic ions that are very useful, and a reminder that for monatomic ions with a charge that is with ions consisting of a single atom, we can predict the charge based on where they are in the periodic table. For instance, alkali metals +1, alkaline earth metals +2. Transition metals, including all metals in this area, they can have different charges. So that's where we use Roman numerals. And also, for monatomic anions, the fact that they end in "ide" is a big clue that it's just a single atom involved in the ion. Okay, so let's do a sample problem. Let's go down to this section here and let's do, what do you say? Let's do number 11. C2H3O2. My goodness, what a formula. But hopefully we'll look at that and then we'll see, this seems to be a polyatomic ion. Let's look for it in our table. We find the acetate ion, C2H3O2, has a -1 charge. So you might want to call this copper acetate. But remember, copper is a transition metal. Copper is in this big central area here where we don't necessarily know the charge. And in fact, in our composition book, it was also one of those examples of an ion that needs Roman numerals because sometimes copper makes a +1 charge, sometimes it makes a +2 charge. So the name of the ion in this case, well, we have to deduce the charge. We know the acetate is -1. Use your scratch paper here. -1. Let me switch to a friendlier color. -1. So we have two acetates, two -1s. So we can deduce, because the charges always have to be balanced, the two -1s are balanced by a copper +2. Copper +2, whose name is copper, parentheses, Roman numeral 2, space, and then the anion is acetate. Acetate. There we go. Copper 2 acetate is the name that goes along with this formula. What's the total number of atoms? Well, actually, there's quite a bit. We have to add them up in this formula. There's different ways to do it, but let's see. One acetate ion, what's in parentheses here, has 2 carbons, 3 hydrogens, and 2 oxygens. 7 atoms. 2 acetates would be 14 atoms. And, of course, we have 1 copper, so that's 14 plus 1 is 15. We have 15 total atoms. How many cations? We just have one. We have 1 copper +2 ion. So we have 1 cation. And we have 2 acetate ions, so that gives us a 2 for the number of anions. Okay, let's do a couple problems from the back. Let's see. How about iron 2 oxide? We also have iron 3 oxide. With these types of problems, you want to translate the names of the cations into their formula. Iron, Roman numeral 2, that's Fe +2. Oxide is the oxygen ion. And we see here in our periodic table, noble gases have 0 charge as an ion, the halogens -1, oxide -2. So O -2. What's our simplest ratio that balances the charges? Well, here it's 1 to 1. FeO is our formula. But what? Let's look at 31. That's Fe +3 with O -2. And here, to balance the charges, we need we need 2 iron plus 3 ions with 3 oxide ions. So that would be formula Fe2O3. So that's why we don't just call it iron oxide, because there's 2 possibilities based on the charge of the iron. We have iron Roman numeral 2 oxide, iron Roman numeral 3 oxide. Okay, our third type of problem is where we are going the other direction. Here, let's do number 48. We have PbNO2 2. Now, NO2, our table tells us that's nitrite. A nitrate ion, it's got a -1 charge. So this has a -1 charge. 2 -1s, the lead must have a +2 charge. And the name for the lead ion, once again, lead is one of those metals that needs Roman numerals. So that would be lead, Roman numeral, the Roman numeral gives the charge, 2, lead 2, nitrite. Nitrite. Okay. In contrast, here is lead with 4 nitrate ions. Since each nitrite has a -1 charge and there are 4 of them, now we must have a +4 lead ion, Pb +4. So this would be a different compound with different properties, lead Roman numeral 4 nitrite. Okay, now any ionic compound is going to have a balance between the pluses and minuses, because ionic compounds, that's how they hold together. Plus attracts minus, minus attracts plus in this model of an ionic compound. This connects to question 55. Can the chemical carbonate be found by itself in a bottle in the stockroom? Why or why not? And the key thing to answer that question is carbonate is a negative ion. If you had a bottle with nothing but carbonate, it would repel itself and it would fly apart. You will never find something that is pure anion, pure negative charges. So that is why you will never find carbonate by itself. I hope this was helpful, and I wish you a beautiful day. Ta-ta. Let's see, where did my menu go?